Welcome to a course on complex analysis. In this lecture, we are going to discuss about Taylor series, right? So, the theorem of the Taylor series is given as suppose that a function is analytic throughout a disk z minus z naught, absolute of z minus z naught is smaller than r naught. Okay, here if you just while explaining the statement of the theorem, let me explain few more things as well, right? So it is given that a function is analytic. Analytic means there exists a neighborhood of z naught. If suppose this is analytic throughout a disk centered at z naught, means okay, let us take f is analytic at z naught. There exists a neighborhood of z naught, that is absolute of z minus z naught, which is smaller than epsilon, right? So this epsilon can now be treated as this r naught. Suppose if your function is an entire function, which means it is analytic throughout the entire complex plane, in that case your r naught can be chosen as large as possible, right? Okay, coming back to the statement of the theorem, this function is analytic throughout the disk absolute of z minus z naught, which is smaller than r naught, and it has a center z naught and radius r naught. Okay, fine. Then your f of z has a power series representation. So what do we mean by the power series? That is a series of this form centered at z naught. Okay, this has a power series representation. This is valid in this disk where your ANs are found using this ideology. Okay, so do we have the any guarantee that the derivative of f exists at all possible derivative exist? Yes, if a function is analytic, then the all possible derivatives exist at the points where the function is analytic. This is what we have seen. If the existence of derivative is guaranteed, then we can divide that value by any value. Therefore, we can easily find this an value, right? And we'll have to prove uh, the series in expression 1 converges to f of z, which means this one converges to f of z whenever the point z lies in the disk that is specified here, right? So this is what we are going to prove. Hope I have said you about what are these things as well. Here if you take just a minute, if you take your z naught as the origin, okay, then the series in 1 is called as Mclaren series, right? We'll prove the theorem to be true for Mclaren series. That is, when taking z naught as 0, we'll prove the theorem, and one can easily extend that ideology to any arbitrary center z naught. Okay, so this is what we are going to prove this one. Okay, here this theorem tells us what if you have the analyticity of a function at some point or throughout some disk, okay, then in the disk you can expand your function as a power series. This is what this theorem tells you, right? So here you don't have to impose any of the convergence test to verify the convergence of a power series that we have, right? If you have an analytic function which is analytic throughout some disk, means this will have a power series representation, and that power series converges to the function f of z in that disk. Okay, remember we have taken only an open disk, we have not taken a closed disk. If we have taken a closed disk and we are talking about the analyticity, then we'll have to check whether this is happening to be true when your absolute of z that is on the boundary, that is absolute of z minus z naught equals r naught. Those are the points. Then we'll have to employ some convergence test to verify the convergence, whereas inside the disk you don't have to worry about it. This theorem ensures the convergence, so we don't have to employ any test to check the convergence, right? Now let us get into the proof. So first of all, let us write absolute of z equals r, and let c naught denote any positively oriented circle. Absolute of z equals r naught, where your r has to be smaller than r naught, which is smaller than your big R naught. So the case that we have considered is, we have a disk here inside which we are identifying some other disk. Okay, this has the radius r naught, and we have identified some point c. This distance is r. Okay, this point is r naught. Hope you get the idea of what we have taken here, right? So this is what we have taken. Now let us proceed. Since the function is analytic inside and on the circle C naught. Okay, this is the circle C naught that we have spoken here. So this is happening to be true, and since Z is a point which is interior in the disk, Z is a point, like we can say Z is interior to C naught, then uh, like since this is true, by Cauchy integral formula we have f of z shall be written as 1 upon 2 pi I integral over c naught f of s upon s minus z ds. We can write like this. Okay, now we just consider the factor. Consider 1 upon s minus z. Okay, this may be written as 1 upon s multiplied with 1 upon 1 minus z upon s. So we can write like this. Okay, and we know that 1 upon 1 minus z upon s, sorry, this one can be written as summation n runs from 0 to n minus 1 z to the power n plus z to the power big N upon 1 minus z. We may write like this, where your z can be any complex number other than unity. So we can write like this. Fine. So let me mark this as equation T1 and this as T2. So by T2, T1 becomes 1 upon s minus z shall be written as 1 upon s multiplied with summation n runs from 0 to n minus 1 upon 1 upon s to the power n plus 1 multiplied with z to the power n. Just a minute. What should we have? We just recall, we must have z to the power n. Whatever we have here, that power n. So it is z upon s to the power n, right? Plus z to the power big N upon 1 minus z. What is z? Z minus s. So z minus s to the power n upon 1 minus z upon s. So this is what we have. So when we take this one inside and this is independent of n, so this goes inside the summation and we have z to the power n upon s to the power n plus 1 plus z to the power n upon s to the power n multiplied with s minus z upon s, right? So this is summation n runs from 0 to n minus 1 z to the power n upon s to the power n plus 1 plus z to the power big N, okay, upon s to the power n minus 1. Am I right? Yeah, hope I am right. Sorry. uh, so this has to go to the numerator, and this is what we are gonna have. Yeah, so this is what we have here, right? So here, now we'll have to take this s also inside, right? So when we take that s inside, we'll have n plus 1. So here we'll have s to the power n. Okay, yes, we are done. Now we mark this as equation T3, right? So this one, let me mark it as equation T. Okay, we have this one. Now multiply f of s with T3. Then we get f of s upon s minus z equals summation n runs from 0 to n minus 1 z to the power n multiplied with f of s upon s to the power n plus 1 plus z to the power big N multiplied with f of s upon s to the power n s minus c. Okay, then this tells us integral f of s upon s minus z dz is integral summation n runs from 0 to n minus 1 f of s upon s to the power n plus 1 multiplied with z to the power n dz plus integral z to the power, like, f of s upon s to the power n s minus z z to the power n dz. So this is what we have, right? So now by the extension of Cauchy integral formula, we have 1 upon 2 pi I integral over c naught f of s upon s to the power n plus 1 ds. This is nth derivative of f at 0 upon n factorial for n running from 0, 1, 2, etc. So this is what we are going to have. We'll have to employ this inside this. Okay, we mark this as T4 and let us note this as T5. Okay, so by T5 are using T5 in T4 integral over f of s upon s to the power n plus 1 z to the power n ds. Sorry, I wrote everywhere dz. It is not dz, it is ds. Integration is with respect to s only, right? So this may be written as z power n as a constant which is independent of s, so we take it outside. So and this quantity simply becomes 2 pi I multiplied with nth derivative of f at 0 upon n factorial. So this is what we have. So substituting this one using T5, we deduce this one, and substituting this in T4, we are gonna have actually T4 becomes integral f of s upon s minus z dz is now you can here you in T4 you have integration of the summation that shall be written as summation of the integration, right? So summation n runs from 0 to n minus 1 integral over c naught. Everything is spoken in c naught, right? So z to the power n, we take it outside. So f of s upon s to the power n plus 1 ds plus integral over c naught, and we have here also you can take that z power n outside. So z power n f of s upon s to the power n z minus s ds. So this is what. So this is to be replaced with this quantity multiplied with 2 pi I. So we have this z to the power n multiplied with 2 pi I nth derivative of f at 0 upon n factorial, plus we have this quantity. So hence 1 upon 2 pi I integral over c naught f of s ds upon s minus z equals. So this is simply summation n runs from 0 to n minus 1 z to the power n nth derivative of f at 0 upon n factorial plus z to the power big N upon 2 pi I integral over c naught f of s upon s minus z. Is that right? S minus z? Yeah. So I have written z minus s. It is s minus z. This quantity into s to the power n ds. Okay. Now what I'm going to do is that I'm going to take this quantity as rho n of c. Let me consider this as a function of c. So what we have is 1 upon 2 pi I. So this is what? This is the function f of z, right? So now f of z has the form summation n runs from 0 to n minus 1 z to the power n nth derivative of f at 0 upon n factorial plus rho n of z, and we know what is rho n of z, right? So now we mark this as what is the running number? We have till equation t5, right? So let us mark this as this quantity as t7 and this as t6, or we mark this as t6 and t7, no issues in it, right? So we have this one. Now the claim is to prove rho n of z goes to 0 as n goes to infinity, right? So this is what we are gonna prove now. Consider absolute of rho n of z. So this is absolute of z to the power n upon 2 pi I integral over c naught f of s upon s minus z to the multiplied with s to the power n ds. So this is what we have. Okay, so we just recall that is your absolute of z is r. Okay, and c naught has a radius r naught with r naught bigger than r. Okay, and s is a point on c naught, right? So then your absolute of s minus z may be written as, which is bigger than or equals absolute of s minus absolute of z which is equal to absolute of r naught minus r. Since r naught is a bigger value than r, which is simply r naught minus r. Okay, if uh, maximum of absolute of f of z is r epsilon is m on c naught, then what happens? So here what I have written is that absolute of f of s is smaller than or equals m on c naught, then absolute of rho n of z, this quantity. Okay, so we have written this as this one. Now we'll just apply uh, the ml inequality, right? So we just take everything inside. So what we are going to have is that smaller than or equals absolute of z to the power n upon absolute of 2 pi I integral over c naught, inside which we have absolute of f of s upon absolute of s to the power n multiplied with absolute of s minus z ds. So this is what we have, right? So this quantity, okay, here we'll have smaller than or equals, this quantity is equal to r to the power n, and this is simply 2 pi integral over c naught, and this quantity is going to be m, and this is r naught to the power n, and this is r naught minus r, and we have ds. So when we take everything to inside, like when we take these things outside, so we are going to have r upon r naught to the power n 1 upon 2 pi, and we have m upon r naught minus r integral over c naught ds. This is the length, right? So length of the circle is simply 2 pi and the radius. So that is going to be 2 pi r naught. Fine. So this is r upon r naught to the power n 1 upon 2 pi. This may be written as m multiplied with 2 pi r naught upon 2 pi r naught minus r. Okay, 2 pi gets cancelled. Then we are left with r upon r naught to the power n multiplied with m r naught upon r naught minus r. Right? So these are the things that we have. Now notice that your r is smaller than r naught. Then your r upon r naught is smaller than 1. Okay, and is a finite positive quantity. Therefore limits n approaches infinity to rho n of absolute of rho n of z, just because this quantity is smaller than 1 and this is a finite quantity, this goes to 0. Okay, this implies limit n approaches infinity rho n of z equals 0. So we mark this as equation t8, I suppose. Yeah, so we mark this as equation t8. So by using t8 in t7, using t8 in t7, we get f of c equals summation n runs from 0 to infinity, I suppose, right? Yeah, 0 to infinity is nth derivative of f at 0 upon n factorial multiplied with z to the power n, and this completes the proof. Okay, so the result is verified for z naught equals 0. Now we'll have to extend this to what? General case. What happens in the general case, right? Suppose f is analytic at analytic in absolute of c minus z naught is smaller than r naught, then f of z plus z naught is analytic in absolute of z minus z naught plus z naught, which is smaller than r naught. Okay, that is in absolute of z smaller than r naught. Take g of z to be f of z plus z naught in absolute of z smaller than r naught. Now you can apply the result for g of z and prove this theorem is holding to be true. So if we mark this as equation T9 by T9, your g of z equals summation n runs from 0 to infinity nth derivative of this one on n factorial multiplied with c to the power n. Okay, now what should you do is that you will have to replace this one. Okay, uh, if you replace, what are you going to get? We are going to get c plus z naught as summation n runs from 0 to infinity f nth derivative. Okay, now we'll have to check what is the derivative in this case. Since f is analytic, f plus translation invariant. Okay, when you translate the function, then also it is analytic, right? So from this you can very well see that nth derivative of z is same as that of these two are same for all positive n. Okay, so what? So this is nth derivative of z naught upon n factorial. Okay, even if we just see what is gonna happen here, then the result is true that f of z equals summation n runs from 0 to infinity, and we are almost done. That's it, right? So this is f nth derivative of z naught upon n factorial multiplied with c minus z naught to the power n. We are just replacing z minus z plus z naught as z. So we'll have to subtract z naught wherever z occurs. So this completes the proof of the Taylor series, right? So in the upcoming lectures, we are going to work out problems on Taylor series. Thank you.